All right. Here we are for the third free response problem in the momentum packet. This one, I believe, is from 2001, I think. So here we go. So here we have a motion sensor set up, and here's a cart rolling along, and a force sensor. And so, and you can kind of see there's like some graphs of velocity versus time and force and time. And like, right away, you're like, dude, force and time? That's like going to be like an impulse sort of thing going on, right? Okay, and coming in a force sensor, like suspicious, it's probably going to smack into it, and you can kind of predict a little bit what's going to come just from the picture. Okay, here we go. A motion sensor and a force sensor record the motion of a cart along a track as shown above. The cart is given a push so that it moves toward the force sensor and then collides with it. The two sensors record the values shown in the following graphs. Okay, so motion sensor, I'm going to get that VT graph. Force sensor, I'm going to get the force time graph. Determine the cart's average acceleration between time is 0.33 seconds. So that's like, yeah, this line here, right? And time is 0.37 seconds. That's here. Okay, and that looks to be pretty much moving along, have a collision, moving along afterwards, right? Look, do you see the velocities go negative here? Yes, it's going one way and then bouncing back. So that's like basically the collision time, duration of the collision there. So determine the cart's average acceleration between 0.33 and 0.37. And so you're going to say, all right, I can do that. I can read velocities off here. I got initial velocity, I got a final velocity, I got a time. I can find an acceleration from that. So taking a look here at part A. Here we go. Find the acceleration. So I'm going to say A, V naught, V, displacement, and time. Acceleration is what I'm trying to find. Initial velocity. To me, it looks like, what do you think? You think that's 0.22 maybe? Yeah, sure, we'll say 0.22. Or should I say 0.25? It's a fourth away. I don't know if it's a fourth away up. We'll say that's 0.22 meters per second. My final velocity at 0.37 seconds, that looks like maybe negative, let's see here, maybe negative 0.18. Okay, looks about right. Okay, and then the time, we're going from 0.33 to 0.37, so that's 0.04 seconds. Okay, and I don't know how far it moves during that. They don't give me any position information there. So this is what I've got. All right, so I want the kinematics equation that doesn't have displacement. That would be V is AT plus V naught. Rearranging this, my acceleration would be V minus V naught over T. And so that's going to be the final velocity, negative 0.18, minus the initial velocity, 0.22, divided by my time, 0.04. And you say, okay, 0.18 minus 0.22, that's going to be like 0.4, isn't it? So it's going to be negative 0.4 divided by 0.04. And you say, hey, that's just going to be negative 10 meters per second squared. All right, assuming I'm doing my math properly. Here we go. We will double check this. So I'm going to go to the AP, it's your College Board's scoring guide, all right, and see how that was supposed to be scored. All right, and the first thing I noticed is, holy cow, they made that worth 6 points? You gotta be kidding me. 6 points for that? All right, let's check. See here. Okay. So, okay. So they say, okay, first of all, average acceleration is the change in velocity divided by the time. So for a correct subtraction to find the time interval, figuring out the time is 0.04. Good grief, they give me points for everything on this problem. Let's just check that. I just kind of right away just stated it to be 0.04. I guess I probably should have said seconds. Anyway, so I'm going to go ahead and give myself a point for recognizing the time as 0.04. Okay. From the graph, picking up the initial velocity is 0.22, and then finally negative 0.18. Hey, I feel pretty good about that. Oh, by the way, notice they gave you a range of values. We looked at it. We were like not quite sure exactly what the value was. They gave you a little leeway reading the graph. Not much leeway, right? 0.22, 0.25. You're like, yeah, you know what I mean? So read carefully. Analyze the graph carefully. From the final velocity, negative 0.18, anywhere from negative 0.15 to negative 0.2. That's a little bit, okay. Yeah, they're giving you some leeway on that measurement. Anyway, they will give you the 0.4. So we're getting a point for each of these values. Getting delta V consistent with the values that you found, right? So making sure that you actually did that that delta V calculation right. Including subtracting in the correct direction, doing final minus initial, not initial minus final. So in other words, the sign matters. They're giving you a point for doing that, basically. All right. And then doing the calculation, the correct substitution of values into the equation, and that's this, right? And then you're having a deceleration, right? And making sure that your final answer, that negative 10 is the proper sign. All right, so that's 1, 2, 3, 4, 5, 6 points. Wow. Feels like, I mean, each of those was actually a little thing you had to do, but some of them seem kind of trivial. Finding that time seems kind of trivial to me. All righty, moving onward. Part B. In part B, they say, can you find the size, the magnitude of the change in the momentum? And you say, well, gosh, the change in the momentum, that's delta P. How do I find that? I don't know the mass of the cart, so I'm not going to be able to do it from like taking the difference in MV, right? Difference in momentum. I don't be able to do that because I don't have the mass. So instead, I'm going to have to recognize the fact that the impulse is the change in momentum, and the impulse would be the area under the force time graph. Because you say, my base formula for momentum, and you should know the base formula for the unit, is this. Integral of f dt, that's the area under a force time graph. That's what we have here, right? That's the change in the momentum, okay? And they say magnitude because technically, if I'm saying that initial velocity is positive, that's the positive direction. The force on the sensor would be in the positive direction, and that's what this registers. The force on the cart would be in the negative direction, wouldn't it? Equal and opposite, force on sensor, force on cart. And that force on the cart in the negative direction is what's going to slow the cart down and then push it back, right? Do you see what I'm saying? So the change in momentum for the cart is in the negative direction. The force is negative on the cart, right? But the sensor is registering the force on the sensor. That's why this graph is up here instead of down in quadrant 4. And they're making it easy so you don't necessarily have to recognize that by just asking for the magnitudes. They don't worry about the sign. Okay, tell you to make it positive. All right, so anyway, we want the area under that graph. I may need to draw on the sketch for this. Again, on the AP, you would have this on your answer part that you're answering. They would have the diagrams there so you could write on them and stuff. But the point is, hey, I want this area. Now, is this a triangle? Yeah, it's not really. Do you see that this is at a certain slope and then it changes angle and goes up like this? This is more like, to me, see, I'm going to write right on this. I would chop it into a triangle here, right? And a little triangle here, a rectangle, and then this upper triangle. So I've got 3 triangles and a rectangle to add to find that area. Okay, so the change of momentum is that area on the graph, right? The area on the FT graph. And so that's going to be, let's see here. This is each of these boxes. See, the 2 boxes is 0.32 to 0.34. Each box is just 0.01. Okay, it takes 2 boxes to be 2. So it's 1/2 0.01 times the height of 10. That's the area of this triangle. That's also going to be the area of that triangle. So I'm going to multiply that by 2. Plus this box, that's 0.02 times 10. Plus the area of this triangle, which would be 1/2 base times height. The base is 0.02. And the height of that triangle goes up to 40 from 10. So that's a height of 30. Okay, that's going to be my area. This axis is in newtons and this axis is in seconds. So my answer is going to be in Newton seconds, which is the right thing for impulse, of course. Anyway, looking at this, let's do the math. 1/10 times 10, that's just 1. And 1/2 times 2, that's just 1. All right. 0.02 times 10, that's 0.2. This is 0.01 times 10. I treated it like it was 0.1 times 10. Sorry, that's 0.0. That's 0.1. Sorry, 0.1, right? Because this is 1/100th times 10 would be 1/10. So 1/10, yes. Okay, anyway, good enough. Sorry, plus 0.2 plus, moving on here, this is, we'll just do this out. This is like 3 times 10 times this. 3 times that would be 0.06. 10 times 0.06 would be 0.6. 0.6 divided by 2 is 0.3. Okay, and that jives. Each of these squares, this is like, yeah, these two together, yeah. I could have done this so much easier. Oh well, there's an easier way of doing this. That's okay. Doing this 0.1 plus 0.2 plus 0.3, you say that's 0.6. Okay, Newton seconds. So that is the change in momentum. If you like, a Newton second is the same thing as a kilogram meter per second, if you prefer. But that's my change in momentum. Okay, and I just screwed up my color coding for showing the scoring. Sorry about that. All right, let's double check and see. So that's my change in momentum because that's the impulse. So let's see. Looks like they say there were 3 alternate methods for solving parts B and C together. Should I solve C and then come back? Nah, we'll just go through what we've got, and then we'll talk about alternate solutions. Here's what they did. So they said, first of all, for part B, 3 points, any indication of the concept of finding the area under the curve. Anything showing you're finding the area under the curve. By like writing that integral out or saying that delta P is the area under the FT curve gets you a point, okay? And, oh, look, I look at that. Okay, think either way, getting the point there. Okay, next, they say for correct numerical value, 0.6. Hey, I did. And then for correct units, I did. Look at that, 3 points for that part. Okay, I feel good. Okay, let's go to part C. All right. Part C says, now let's find the mass of the cart. So if it were me, I want integral f dt as delta P is what I'm going to do. Because I'm going to say the mass of the cart, that's going to show up in the momentum equation. I just found out how much the momentum changes by. And I know the velocities, right? So I would probably solve it that way. So I'm going to use that idea that the impulse is equal to the change in momentum. And so the change in momentum, that's P final minus P initial. So that would be mv final minus mv initial, or if you like, that's mass times the delta v. Yeah. The impulse, again, we know the impulse is that area under the graph. The area under the graph is what we just found there. The mass is what we're trying to find. Delta v, that's just the final minus the initial, which we calculated up here, v minus v naught, and got negative 0.4. So you're like, oh, okay, my impulse, before they found, now be careful here, this was the magnitude of the change in momentum. So we made it positive, but this was just the impulse. Technically, this was the impulse on the sensor. We want the impulse on the cart. I need to make this negative 0.6 for this to mathematically come out right. And the delta V, because the cart, the change in V was negative, right? Negative 0.4. So those two negatives are going to cancel. They better, because I need to get a positive mass out, don't I? So when I do this, 0.6 over 0.4, that's just 1.5 kilograms would be the mass of the cart. All right, so that's my calculation. Let's go ahead and see what College Board thought people would do. Okay. College Board said this was worth 2 points. So first of all, any statement of the correct equation for the change in momentum. Delta P is m delta V. Oh, look, it's right there. Look at that. I substitute that in right there. Okay. And then for correct substitution of values, right? Yeah, delta P is the impulse we found before. So just taking delta P divided by delta V. Yes, that's exactly what we did. Yeah, 0.6 over 0.4. Yep. We did it. We did it there. Okay, so that's it. That's 2 points. Okay, now, how else could we have solved this? Well, they're suggesting here, express the change in momentum in terms of average force, that delta P is average force times time. And then for some method of using the graph to find the average force, indicating that the area is equivalent to 6 boxes with a height of 10, so the forces. Okay, yeah. So I was thinking about another technique. That's probably that's the third technique. So they're saying, hey, I'll just take the average of the force. So what they're saying is to find the average force, you might notice that if I took this triangle and this triangle, that makes one box. And if I took this triangle and, see, splitting it down the middle, this triangle would go together to make 3 boxes. So I'd have 1 box from these little triangles, 3 boxes from this triangle, and then 2 boxes here. So that's 1, 2, 3, 4, 5, 6 boxes. Each box is 10 times 0.01. So each box is 1. Wait, 10 times 0.01 is 0.1. 6 boxes, each one's 0.1 Newton seconds. So it'd be 0.6 Newton seconds. I'm sorry, what did I just do? Oh, so I'm taking that. Oh, okay, so they're saying force times time. So I'm doing then that 0.6 would be the average force times that, multiplied by that time. The time is 0.04. So what I'm getting here is that 0.6 is the average force times 0.04. And so if I take 10 times 0.1, yeah. So I take 0.1 times, anyway, but that's the, so basically they're saying, basically we're getting that average force then, what are we doing here? Area is 6 boxes with a height of 10. Yeah, right. Yeah. All right, we're just finding the average height, right? That's really weird the way they did that there, frankly. That's really strange. Like I said, it's like 6 of these boxes. And so I see. So if I just stack them up, right, all that area, if I stacked it up, it'd be a height that was 60 with a width of 0.01. But I'm actually spreading it out over 0.04. You know what I mean? Over 4 of those boxes. So they're dividing by 4 to get 15. That's weird. That's a weird way of thinking about it. But okay, whatever. Point is that average height of 15 newtons, average 15 newtons times 0.04 seconds, give them 0.6 Newton seconds. Yeah, I'm not a fan of that. I mean, I guess it works for this case. If this was a curvy graph, I don't talk about it. So anyway, they give 1 point for that. And once you have that, for the impulse, right? So that's another way of solving for the impulse. That's weird. Okay. Okay, now then finding the average force in terms of average acceleration, you would say F is ma, and then the acceleration we got before, the average acceleration, we found that in part A. So just taking the average force we just got divided by the average acceleration to get the mass. Okay, so that's another way of doing it. Method 3, which I think is going to be the method I like better. Method 3, they say, this is the same page I showed before. Here we go, sorry. Method 3, we're going to find the force because we can say, oh, here, look. Look at this graph. In that time from 0.32 to is that we're looking at 0.33 to 0.37, right? Bink to bink. I can go ahead and I can say, look, there was a change in V here divided by the time. It's like I'm finding the average slope here would be the acceleration. The slope of a line connecting the start to the end, that slope would be the average acceleration. So, so I could say, well, yeah. And then the average force, again, we find the average force here to be 15. And then we take that F is ma, force is mass times that average slope there, right? The slope connecting the start and the end points between here and here, right? The slope of that line would be the average acceleration. So then I'll take those and take the force divided by the acceleration to get the mass. Okay, and that's what they did here, yeah? Yeah. Yep. Okay, that makes sense. All right. Yep. Okay, so they're saying that here they would find from that slope and the acceleration we found before, right? Yeah. Finding that average force from the area there, right? And then finding the mass from that. Once you have the mass, then they went back to do part B to find the change in momentum. Now that we had the mass and the two V's, we could find that real quick. Okay, so that's that one. Okay, weird. Yeah. I definitely prefer my technique. Okay, and then there's one more part to this problem, and that is determine the energy lost in the collision between the sensor and the cart. Well, now that we know the mass, right, we can do an energy calculation before the collision, after the collision, and we can say, I'm going to do that in here. We'll do part D. So we do our little sigma W is delta K plus, you know what, I'm not going to have anything else. I'm just going to have kinetic energy, right? There's no springs. So my system here is going to be the cart, right? Well, we'll do the cart and the sensor together, right? Yeah, the cart and the sensor. Yep. Cart and the sensor. Comes in, hits, bounces back. Sensor stays put. So there's energy in the cart, kinetic energy in the cart at the start, kinetic energy in the cart afterwards. Those kinetic energies won't balance out because some of the energy went into wiggles and jiggles and vibrations from that collision with the sensor. So that's the idea. So that work here, that's the energy, that's the change in the work is the change in the energy of the system. This is what I'm trying to find. That's the change in the energy of the system. It's just delta K. So it's the kinetic energy at the end minus the kinetic energy at the start. So that change in energy is that energy that was lost to vibrations that went to that form. Final kinetic energy, that's 1/2 the mass of the cart times the V final squared minus 1/2 mass of the cart V initial squared. I know values for all this stuff on the right. So that energy that went into thermal form was 1/2. The mass of the cart we just found was 1.5. The final velocity, I just read off the graph, that was a negative 0.18. Minus 1/2, 1.5. V initial squared. V initial squared we read off the graph to be 0.22. Again, your values, if you read off slightly differently on the graph, these values might be slightly different, and they would take that into account in the scoring, I'm going to presume. So doing this then, the energy that left my system went to thermal energy, I should say, that left is no longer in kinetic. I'm going to just grab a calculator for that. I'm not going to try to do that in my head. I've been screwing up my mental math today. I don't know what the deal is. So I do this 0.5 times 1.5 times 0.18 squared. Again, that negative is going to go away when I square it. Okay, minus, that's not going to go away. 0.5 times 1.5 times 22 squared. Oops. Don't you hate it when you put in parentheses you shouldn't? Okay, anyway, I got this negative 0.012, and my unit on energy is going to be joules. Okay, so let's check that. All right, here we go. Well, that looks good. All right, they say this is worth 4 points. Correct statement of energy change. The change in energy is the final minus the initial. Are you kidding me? Basically, that's this. Change in energy is that final minus initial kinetic. That's really lame. Whatever. They're given a point for that. That's really weird. Okay. A point for using the kinetic energy expression here for either of these terms. For correct substitution of values consistent with what you did above, including the squared velocities, yeah, that you're subbing in values right throughout this mess, basically. And then your answer with units. All right, there we go. So that's 1, 2, 3, 4 points. And you say, okay, checking through here. So here we got 6 points, plus 3 is 9, plus 2 is 11, plus 4 is 15 points. And that's that problem.